Today you should have the first couple of quizzes done, although no points will be taken off until 9/11. They still have time. But we're going to talk about assembly. And even if you take quizzes late, you can still take them. I'm only going to take a couple of points off if I can remember to do that even. The only reason I punish people at all for being late is just to encourage them to keep moving. So let's talk about x86 disassembly. So we talked about basic static analysis, where you look at malware from the outside without looking at the code. Things like the hash, and dynamic analysis, where you watch it go. And now we're down to disassembly. By the way, one important fact, I think I'll pause to write on the board. I decided to rearrange the chapters this year. IDA Pro scares people, and I decided to put it off till later because, in fact, ALI debug is easier to use than IDA. So it is not logical to have IDA followed by ALI. I put ALI first. So the chapter order has changed. So 9/11 is quiz on chapter 8. I should probably try to write that a little better. But I moved the chapters out of order, which is something I don't normally do, but I'm trying it this semester because the older order seemed a little bit hostile to the students. Then 9/18 is chapter 9, and 9 and 25 is chapter 5, and then chapter 6 and chapter 7. 5, 10. Just take a note of that. I tried to get everything updated in Canvas, so hopefully it'll tell you the truth, but I decided to move 8 and 9 up here before 5, 6, and 7. And I'm writing the projects to follow that pattern too, so that you don't jump into IDA until after you've already used ALI, because ALI is more fun. Yeah?
How are we getting our hands on IDA? Is there a trial or something?
Oh, there's a free version. There's 2 free versions, in fact. There's a pay version that costs like $5,000 bucks, but the free version is good enough for what we're doing. Okay. What happens is the free version works for 32-bit x86, and the pay version works for other things. And well, I'll settle for x86. That's a very important point. In fact, I proposed to give a talk about this at DEF CON, and they actually rejected it on the grounds that IDA wasn't free, and I felt abused. But anyway, if you ever submit a talk to a conference, be aware that if they reject you, it doesn't mean there's anything wrong with you. Because I've been on the reviews, and often the review board has no idea what's going on, and they make mistakes. Same thing for job interviews. If you apply for a job and you don't get in, don't imagine that there was a fair consideration of applicants and the best people got in. It's often very, very far from that. Don't take it personally. It's very likely that there was a political move and the project that was going to hire somebody got canceled, or somebody's cousin needed the job or something like that, you know. That doesn't mean there's anything wrong with you when you don't get it. Just keep knocking and wait for the random factors to align. Anyway, so there are levels of abstraction of code, and this is really important. Typically, the people that write code write it in a high-level language like C. So they're writing instructions like print and exit. Then they run through a compiler that automatically reduces that to machine code. The only thing the processor ever runs is this binary machine code, just raw binary. Now, the malware analyst would like to use high-level language, just like the original people who wrote the malware, but they can't, because this is why people like to use C for commercial software and for malware, because you cannot get back to the source code from the compiled code. All you can do is get partway back to this stuff called assembler, which we've been talking about. So the malware analyst typically has to learn how to use assembly. And this is why when I went through the bureaucracy here to get this course approved, they complained because I was teaching debuggers. And the CS department said, oh no, we own debuggers. And of course, what they're talking about is source level debuggers that debug this stuff. They aren't imagining that anybody would do this kind of debugging, because you'd have to be a masochist to torture yourself by trying to debug things at this level. But that's what malware analysts have to do. But real programmers have source code, and they don't look at the assembler. They're afraid of it just like everybody else. Yeah?
So in other words, at that level, the assembly, you can debug that to a lower level? Is that what
No, but you can analyze it and figure out how it works, and you can modify it to change how it works. You can do programming at this level. It's just a waste of human life. I mean, it will take, you'll spend 100 hours writing a program that would have taken like 1 hour in a higher level language. But you actually know what's going on. That's why the assembly language programmers are like real proud of themselves, like the kind of people who build their own cars. You know, they feel really better than the other people who just buy a car and drive an automatic transmission. Oh, those people are just scum. Real men build their own car. It's the same way. I've been going through some of this today, some of the old assembly language guys, and these guys are like an elite. And I imagine a lot of them are women too. I don't mean to be sexist about it. Yeah, but it's a real advanced skill, and people are real proud of having it. Like if you go in Cisco, it's subnetting. They'll brag about subnetting. Oh, I'm cool, I know subnetting. Those other people are just scum because they don't know subnetting. Anyway,
Quick question.
Away?
yeah.
So when they're compiling the malware,
Yeah.
there's sometimes you can compile it like with strings, without strings, because some of your projects are
Yes.
with string.
You almost always,
For a second.
yes. When you compile it, the default is to remove all links to the source code and all the strings, so all you get is meaningless numbers. You store something in a location, and every time you refer to it just by the address of the location, you remove the meaningful variables. You have to use a special compiler flag to retain connection to the source code. That's the -G in my exploit development class to keep the strings. If you do that, then you can do source level debugging, which is the way a normal software developer would do it, so they can actually work with this kind of code. But if you're trying to make software to distribute and sell to people, and you don't want them stealing your code, or you're making malware, you want to remove the strings. And therefore, every year or so, you'll see a news article about this piece of malware was actually distributed with strings, because the person who wrote it was such an idiot, they forgot to strip out the strings. And that makes it much easier to analyze.
So the stuff we'll come across in real life will likely not have strings.
Almost always it won't, yes. So a few of my projects, I put in the strings just to make it easier. But normal malware, you don't have the strings. That's why you have to work at this level. And when you work at this level, all you get is meaningless addresses for everything. Nothing has any meaningful names.
And that's why, like IDA Pro, you can add labels and stuff.
Right.
So
IDA
you
Pro
start-
expects you to add those labels manually.
So that way you can start to make sense. Okay.
Exactly. Good. So here's levels of abstraction. You have hardware at the lowest level, then there's microcode and machine code, low-level languages, high-level languages, and interpreted languages. That's the general levels of abstraction. The hardware itself is just transistors, and, or, and not, XOR. These are the fundamental operations, and if you've taken a digital electronics class, you actually take diodes and ANDs and XORs, and you build things out of it that will do things like add numbers, and that's what's going on in the processor. Just millions and millions of little transistors doing simple little bitwise calculations. One bit combines with another bit to create this output on a truth table. All right, that's the hardware. Then there's microcode inside the processor and various things that run here. We're not going to mess with that. There's other layers of code above it. This is, I think, also in the firmware on the motherboard. By the way, I should mention in passing, there are bugs in the hardware. There are 100 known bugs in the Pentium 4, and I'm sure the later versions have even more, in the hardware, which can never be patched. And they try to patch it in the microcode on the motherboard. So this is what's, and now of course this happened to the whole world because of Spectre and Meltdown, which proved that there is a fundamental design flaw in the logic underlying all modern processors that cannot be fixed. So we are patching it by trying to patch the operating system to try to stop the attacks that are currently in use exploiting it, but it is a losing game because we cannot really patch the fundamental hardware underneath.
So there's no firmware updates for PCs.
I haven't heard of a firmware update. What they've been doing is patching the operating systems, and that has turned out to, yeah, in principle, I would think patching the firmware might help too, but I haven't heard of anyone doing that. The problem with patching the firmware is it would depend on the brand of your motherboard. So you need a patch for each one, like BIOS updates, and that's not as popular as a general patch for like all Windows, but that's certainly one direction to go. In the long run, we're going to have to replace all the hardware.
You do like firmware updates on routers and
You do.
on switches.
You do.
And security appliances.
Absolutely, and there are BIOS updates for the motherboard, and I would think there might be like firmware updates for chips on the motherboard to deal with Spectre and Meltdown, but I have not heard of them. Yeah,
Yeah, I think Intel's solution for the 9th gen is just remove hyperthreading and remove speculative execution altogether.
well, see, if they do that, they're going to have like a 50% or more speed reduction.
Right, yeah.
That's what they've been reluctant to accept.
Yeah.
Of course, one way to look at it is that way they'll sell more processors. You have to have 2 processors and everything, but I don't know if
What did you say, remove hyperthreading?
hyperthreading, speculative execution. Yeah, speculative execution is the real problem.
Altogether.
Yeah. Anyway, well, you know,
running instructions.
I was reading a paper about it today. Realistically, it would seem like all you have to do is thoroughly clean up the results of speculative execution. But anyway, they're currently arguing, yelling about what to do.
It seems to me we've been doing speculative forever.
We have been doing it for like 20 years.
20 years at least.
That's right, and it's been vulnerable for all this time, and people didn't figure it out until about a year and a half ago. And they kept it secret for about a year so that they could produce the patches, and the patches were still complete garbage, causing a blue screen of death. So that was an example of very limited responsible disclosure that, as far as I can tell, pretty much failed. It did not result in all of us getting a good patch. The most successful example in the world that I know of responsible disclosure is Dan Kaminsky's in 2008. He found a vulnerability in an entire protocol of DNS worldwide, and he managed to reach the right people secretly and get it patched to where, as far as I know, no major attacks came from it. That's the only time I've really seen his work.
Wow.
In the past, either the secret leaks out too soon, or the people that are supposed to patch it in secret don't really patch it, or some stupid thing happens, but he managed to actually get it done. That's very rare. And there was some kind of scandal at the time that it did leak out a little sooner than somebody thought it should, but the end result was there was no huge DNS attack on the internet that did a lot of damage, and there certainly could have been. Anyway, so your machine code, you got opcodes, which are the verbs, essentially, tell the processor what to do. And so there are human readable languages that attempt to make it easier to read the machine language. And that's what this push and pop and nop is. The processor does not know a push and a pop and a nop. All it sees is binary, but the humans refer to the instructions this way, and that's what a disassembler creates. It takes the compiled binary language and it creates this assembly code that is more human readable than just strings of hex characters, but not a whole lot more readable. And of course, most people would rather use C, C++, Java, Visual Basic, Python, and things like that. And the highest level is interpreted languages, like the way people use Python in interpreted mode instead of compiled, where you type one line of code and it happens right away. You're not even like structuring a file. That's the closest to meeting human flow. Do this, well then do this, then do this. I don't even need to like have branch statements or anything. But anyway, these are high-level languages that run through layers of translation, like the Java virtual machine. You write this high-level language, it goes through layers of translation to get back to the binary. It's very much like someone, probably C is like driving an automatic car, where there's a gear shift doing for you, and languages like Python are like being the boss, telling your programmers, write a program that will do this and figure it out. You have a very high-level abstract leaning, and layers underneath you make all the detailed decisions, which you don't really control anymore. So if you write a Python thing and you reserve some space for an array and then you put in more stuff and it gets bigger and you say, well, how many bytes are reserved for that? You don't even know. It's not obvious at all. You probably don't care, but if you did care, you'd probably wish you were using C or assembly where you'd really know what was going on. So this is the process of reverse engineering. Having a finished product like a virus that somebody made that does something, and you have to figure out what it did out of the box. That's why they put a picture of an alien on the cover of the book. This is the classic issue of extraterrestrial technology from science fiction. They say, suppose a UFO crashed, what would we do? We would have to take the finished product and just reverse engineer it to figure out how it worked. And so this, as far as I know, is not happening with alien technology, but it is certainly happening with malware. You're getting stuff that was produced by thousands of hours of brilliant people in a country like Russia where they have highly paid programmers that just work all day writing malware. You get this thing and now you have to try to figure out what it does, and it often does very clever things to hide from you because they play chess for fun over there. Very often you will find that they have thought 10 moves ahead. They have thought of the 10 things you're going to try, and they put a booby trap in each of them to frustrate you and make you give up. So IDA-Pro is the main tool used for this, and there are different assembly languages for each processor. We're mostly, in this class, I think you're going to do nothing but x86. In my other class, I've got a bit of 64-bit, and now I've got some ARM in the 127 class. I was real happy to get that working a couple days ago. But there are many other things out there, and ARM is the future. Intel seems to be on the way out. Everybody is abandoning Intel. I don't think it's because of the speculative execution flaw. It's really because it consumes too much power and uses up the battery too much and makes too much heat. It turns out that ARM gets more calculation for the same amount of electricity. And that turns out to make a lot of difference. So Apple is moving to ARM on their PCs, and the servers are moving to ARM from Intel. So that's why I'm very happy to be moving into ARM assembly. That's where the future is.
Who makes the ARM processor?
Yeah, the ARM processor. Yeah.
But who makes it?
Who makes it? I think it's AMD.
Okay.
Well, I don't really know. Anybody know who makes ARM?
They subcontract out
Yeah, I'm not even sure it's just one company. I think it's like a standard. And anybody,
The fab is TSMC. There's other company manufacture subcontract out.
so it's not controlled by just one company, is it?
The design group is in England. They only design the chip, and manufacturer is something else.
Okay. So that sounds open, sort of like the IBM PC, where they designed it, but anybody could
So
make
the
it.
fabless type.
What's the name of the company?
Fabless type company.
Then?
It's ARM company, but
It's
the
the name of
type
the
company, the type of chip they do is like fabless. That means they don't own the fab.
Okay. Anyway, it's a good question. I don't know. Anyway.
That have designed chips with.
So anyway, here's the general structure of this. You got a CPU, which is what actually does the mathematical operations on code, and it's got to take data, typically from RAM or maybe other things like the hard disk and network card. It's got the two parts in here, there's three parts. There's a registers, which are little pieces of memory storage on the CPU. So they are very fast. There's a fundamental problem in all of computing, which is you have multiple devices that have to work together that run at different speeds. So your CPU is blazing fast, like 3 or 4 gigahertz. Your memory is very slow, like maybe faster now, but I used to hear numbers like 80 nanoseconds if you ask for a piece of RAM before it comes out. So that's like 80 times 4 cycles of the processor, 320 cycles. It's waiting for the RAM to cough up the data. And the hard drive is 1,000 times slower yet, and the user is 1,000,000 times slower yet. So often the processor is ready and it's tapping its foot waiting for these slow other things to cough up the next data to work on. And that's why things like hyper-threading are logical. It might as well be trying to do 20 things at once, because it'll send out 20 requests for the next data, and whichever one finally coughs up the answer, it can work on that one while the others are still waiting for all these slow devices to catch up. And that's why you have buffers and queuing and speculative execution and all these tricks to somehow avoid wasting the time of this processor, which is ready for more work and can't get what it needs to do it. So one thing you do is you put the data here in registers on the CPU, which are really fast, but you have only a small amount of space here because it's expensive to put more storage here. And so then you have a control unit, which is responsible for keeping track of which instruction you're processing, fetching the instruction from RAM and loading the instruction. Then you have the ALU that actually does the math. XOR and 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 multiplication and all the things on it to put out the answer. And then it sends it out to the I/O devices, like the screen and the keyboard. So that's the general structure. So the control unit fetches things using the register called the instruction pointer, the EIP in 32-bit code, the PC on ARM, the RIP in 64-bit code, but it's a pointer which points to the address of the instruction currently being executed. Then you have most of the instructions work on data in registers. In fact, the Intel has a lot of ability to work directly on RAM, but ARM does not. If you want to do anything in RAM in ARM, you have to first load it into a register, calculate it in the register, and then write it back out to RAM. It's explicitly required. It takes like 3 ARM instructions to do what's often 1 Intel instruction, and that is by design as the general philosophy because ARM is a RISC system, which is kind of funny. Apple started on Motorola RISC systems, reduced instruction set computing, where it has a small instruction set and they try to make it really fast. And then they moved to Intel, which is a CISC system, complex instruction set computing, where they have 10,000 instructions, many repetitions of the same instruction. And now they're moving back to RISC with ARM. So this is a huge tectonic shift in computing. People have been proponents of the reduced instruction set or the complex instruction set, and they have sort of, like the Democrats and Republicans, they've been lead at different times. And so now we're going back to RISC. The main memory is what you quote when you say your machine has 4 gigs of RAM or 8 gigs of RAM or something. That's your main memory. You start at 0 and go up to 8 gigs. And as each process has its own regions used by it, like a part for a stack, part for heat, part for code, and part for data, and there may be other sections. And the portable executable files we'll talk about have standard names for these, like .text and .data and .r data. And each process has its own stack, which is just not different than any other RAM. It's just the RAM reserved for that one process to use. And it uses virtual addressing. All Windows programs believe they are loaded at 400,000 hex. They work on that address. I don't know why, but that's where they think they are. They can be anywhere in memory, but they work with the virtual address from that point, sort of like a virtual machine. And they're only allowed to access their own memory, not the memory belonging to another process. Data is put in here. You can have static storage and data. The RAM, of course, is not intrinsically static. It can be changed at any time, but it is be determined by the operation of the operating system that certain static variables will not be changed while the program is executing. And those, you can have global variables that are available to any part of the program, and you can have static variables that are not allowed to change during the operation of the program, or you can have the normal kind of variable, which is local to one routine and can be changed at any time. So code are the instructions, but I probably mentioned it before, maybe not in this class. The fundamental reason why computer exploits exist is because the processor does not know what it's doing. So it doesn't know if the bytes are images or movies or text or code to execute. So you can put in something that at one level of processing is perceived to be text, and at another level you perceive it as instructions to execute. That is the fundamental problem. It doesn't have any type bit on this, which seems to me like an error. You could have made it so there were like 10 bits in every byte, and 2 of them tell me what this is. Is this code or text? And that would have ended a whole generation of exploits if they'd done that, but that's not where we are. Where we are, there's just bytes, and they can be interpreted as one way or the other. And that leads to all these crazy exploits. So the heap is dynamic memory. This is where you store things that you're only going to use temporarily and then throw away, like if you're processing network traffic because you're an email client. You'll read in some packets, store them, process them to dig out the part you want, and then throw them away and read in more packets and put them on top of that space. So you want to allocate space, use it, and then return it for reuse. That's what the heap is for. You have chunks of any arbitrary size, and you can allocate a chunk with malloc, and when you're done, you free it with free, and the data RAM is now available for another chunk. The stack is where you put local variables. The stack has this particular last in, first out structure, which is specifically designed to handle subroutines. So you have a main, you have the operating system running, you launch a program, it is a subroutine running from the main program, a child of it, then it calls a subroutine, then that calls another subroutine like to print something, and this requires you to repeatedly do this process where you're running one routine and you want to stop and execute a subroutine, and when it's done you want to return and pick up where you left off. That is the process the stack is designed to facilitate. Yeah?
I have a question. So in languages like Java that have garbage collecting, does that operate on the stack?
That have what?
Garbage collecting?
Garbage collection.
Yeah.
Yeah, I can't say exactly what Java does. I do know there is a question of heap fragmentation and defragmenting the heap. And I know in SSDs there's a garbage collection which removes the unused parts of the SSD. I don't know exactly what level the Java form works. It is another big issue, that if you have areas where you keep writing and changing things, just like your hard disk, they do get fragmented. And then you want to have some kind of process of accumulating the empty space into one big block for efficiency. It's a good question. I don't know where the Java level is. If anybody does, feel free to bring it up. Anyway, so here's your instructions. Mnemonic followed by operand. So here's move is the most common instruction. Move ECX 0x42. This will move data into this location from here. If it's a number like 42, that's called an immediate constant. It means the literal number 42 in hex is put in the ECX. This is the standard way Windows programs are written in this, which I think is the Intel syntax instead of the AT&T. I might have them backwards. The one where the destination is here and the source is there. That's the most common way you see Windows code written. Linux code is typically written the other way, just to keep you guessing. But anyway, by the way, this is considered sloppy and undesirable to refer to constants in this fashion because the move operation is 32 bits in size. So that 42 is actually this. 1, 2, 3. I think got too many zeros there. Let me fix that. That's very annoying. I don't want you. It's on 32-bit, which means there. There. I think it's right now. Let's see. It should be, what is this 9 doing? I'm losing my mind. All right.
Move ECX.
What is that 9 doing there?
It's a
That's the
move.
move.
It's the opcode for the move.
Oh, the op. Oh, thank you. That's the move. Look here. So this is the opcode. This is 1, 2, 3. Okay, one more 0. 4 bytes. That's what I want. This is 1, 2, 3. There. Now it's right. So there are 4 bytes in 32-bit and 2 hexadecimal digits per byte. So it's 42000. And this is little endian. So the 42 is the number of ones. This is the number of 256s. This is the number of 65,000s. And this is the number of 16 millions. So that's the way Intel stores things, little endian first. And the move is B9, so this takes 5 bytes to do that, and a bunch of them are 0. That's what happens when you use literal constants. All right, so you have a mnemonic, a destination, and a source. Move ECX 0x42. This is Intel. AT&T is the other way. So Bigendian is really the most significant byte first, which is the way a normal mathematician would write thing, where you have 42 as the number ones, then you have the 256s here, the 65K here, and the 16 million there, just the way you do with normal numbers, where the more further left you go, the more significant the bytes are. For some reason, Intel uses little endians, so the bytes inside have the usual order, where the bit on the far right is 1s, the next bit is 2s, 4s, and 8s, but then this is more significant, and this is more significant, so it does not map down to a normal mathematical base 2 or anything. It's a weird structure, where inside each group of 8 bits, the one on the left is more significant, but the bytes, the one on the right, is more significant. Very strange, but that's the way it is. IP addresses are not stored little endian, and this is really important because the entire structure of the IP version 4 system was intended to make it possible to route packets before the addresses come in completely. So that's why the first bit tells you if it's class A or not, and the next bit tells you if it's class B or not, and the next bit tells you if it's class C or not. That was the plan. With CIDR, it hardly matters anymore, but the original plan of the internet was designed to be so fast that it could work on packets before they'd even finish coming in the card. Anyway, that's why it does not take the most significant bit and put it at the end. It puts it right at the front because that served to provide efficiency in the really slow early internet 20 years ago, and it became the standard. So there's immediate values like 0x42, then there's registers, of which you only have a few, EAX, EBX, ECX, and so on. And then you got memory addresses. If you want to refer to someplace in RAM, you put an address in brackets. And this could be an immediate value, or it could be a register. If it's a register, then you take the contents of that register, which are 32 bits, and you interpret it as an address, and go get the data from that location in RAM. So the square brackets indicate indirect addressing, what C also calls pointers. All different words for the same thing. So you got A, B, C, and D registers. Yeah.
So on the previous slide, is there any limit to like the expressions that you can put in there? Is it usually just adding, subtracting, and multiplying?
There are serious limitations. Even with the Intel, the question is, can you put any kind of expression in here you want? And the answer is emphatically no. This is a huge problem. The point of the Intel complex instruction set was that you would have many, many instructions, like register plus constant, constant plus constant, register plus memory address, and all that jazz. And you have a lot of them, but not all of them. Frequently the one you want, you don't have, and you have to use several instructions. First put it in a register, then put it down here. And in the reduced instruction set computing, it's almost always the case that what you want to do, you cannot do with one instruction. You have to combine several instructions to do it. You would think with 10,000 instructions, everything you need is there, and that is absolutely not true. Very often, you can't do what you want in one instruction. You have to combine 2 or 3 to get the effect you want. So here's the general purpose registers, A, B, C, and D. They can all be used for anything. The only thing is, by convention, typically when a subroutine returns, it puts the return value in EAX. You know, when you see, you call a function like print, and when it returns, it'll tell you 0 if it worked and 1 if there was an error. That number is typically in EAX. Here's the stack. The top of the stack is ESP, and the bottom of the stack is EBP. You don't want to use those for other purposes. Those are reserved for that purpose by almost all code. So you don't mess with those unless you know what you're doing. And the ESI is an index used to count through an array, and you can use it pretty much. People use it to count through strings they're copying and such. And then there's E-flags, which people rarely refer to directly, but it includes a series of individual bits that record whether the last computation resulted in a positive number, a negative number, a 0, or an exception, other conditions. So when you're branching on equal, branching on not equal, it's actually looking in here to see if the last operation was equal to 0 or not. And of course, the extended instruction pointer, which is super important, which controls program flow. So that if you somehow gain control of EIP, it's very easy to take over the box. So that's the point. That's all this is saying. They're all 32 bits in x86 processors, which is what we're talking about here. And x86 code running on x64 machines runs that way. There are some legacy instructions that refer to the older stuff. You can refer to 8 bits, A low and A high, of these things. You can do 8-bit processes if you really want to, and you can do 16-bit processes. Now, normally there'd be no reason to do any of that. The reason you do it is because, we'll do it in 127, because you're trying to write shellcode, which is attack code that hides inside a string like a password, so you have to have no nulls in it. So you can't have those 32-bit values that have all those zeros in it. So you have to actually use these old legacy instructions that move only 8 bits at a time to avoid those nulls. Other than that, there's no conceivable use to them except if you wanted to play like an MS-DOS game on your modern machine or something. So that's the game. Here's EAX. Here's AX is the lower 16 bits, and then there's A low and A high are the lower and higher 8 bits of the 16 bits. So you can move 8 bits at a time if you want to, but there's normally no reason you'd want to do that. So those are your general registers. They're pretty much interchangeable. Their multiplication and division actually use special references to these registers because, of course, if you multiply two 32-bit numbers, the result might be bigger than 32 bits, so you have to use another register for the overflow. And division is floating points. By the way, there's a whole floating point unit and a whole different floating point set of registers, which we almost never talk about. The only people that would care would be like graphics people who want to do 3D rotation and stuff. But it is actually a pretty cool place to hide things. I've seen it used by CTF problems and malware. It's a good place to hide something. Put it into floating point registers. Gave me a headache the first time I saw it. I thought it was some kind of typo. What's that? I had to go find out what they were and how to see them. Pretty good place to hide secrets from disassemblers that don't know about them. Anyway. So the E flags, like I say, a lot of flags there, individual bits. There's 0, carry, sign, and trap. The trap flag is what's used to break to the debugger. This is what breakpoints are. The trap flag means you have hit a trap bit. So the instruction pointer points to the next instruction to be executed. If you have something like a buffer overflow exploit, you get an opportunity to change the EIP. So you usually notice that the program will crash. If you just put in a long name for the password or something, it'll put random letters like capital A's in here, and that points to an invalid address, so it will just crash. And then you have to improve your exploit to where you put in something carefully chosen here that instead of just crashing, will give you control of the box. And that's the whole point of the 127 class. Here, we're on the other end. The bad guys have already done that, and we're trying to take apart their code that is doing that sort of stuff to us. All right, so here's some simple instructions. Move is your most common instruction. Move source to destination. That's the Intel format. And remember, indirect addressing is indicated by square brackets. So if you move EBX to EAX, it'll take this 32 bits in EBX and put them in EAX. This will take the immediate value 42 and put it in EAX. This will take that memory location, whatever's in there, and put it in EAX. By the way, here's one of the many cruel things. This memory location counts the bytes. And then it moves 32 bits. So it takes the byte C4 and the next three, C5, C6, and C7, and puts them all in EAX. Because the addressing is done by bytes, but the processing is done by words, and in 32-bit processors, a word size is 32 bits. So it is pretty annoying. In a more logical world, when we went from 8 bits to 16 bits and 32 bits, it seems like they ought to have just changed the byte size to 16 or 32, but that's not what happened. Anyway, this will take the EBX, interpret it as an address, fetch the memory from that location and put it in EAX. And here's one of those calculations you were talking about. You can take EBX plus ESI times 4 and go to that location, and this is so you can copy a string. So you take 4 characters at a time, put it in EAX, then you increment ESI, you get the next 4 characters and put it in EAX. This is how you'd copy a whole block of data from one location to another, which is very commonly done. And then there's a thing called load effective address that seems nuts. When I first saw this, I thought it was stupid. So you take EAX, you calculate the address EBX plus 8, and then you load the address. So all you do is EBX plus 8. And I said, why did you even bother to call it an address and then pull the address? Well, the reason is because the instruction to load EAX with EBX plus 8 doesn't exist. You might want that, but you can't have it. So this is how you do it. Kind of nuts. Otherwise, you'd have to have 2, if you have to load EBX into ECX, then add 8 to ECX, then put ECX into EAX, or something like that, would be the way to do it with multiple instructions. So anyway, this is what moves the data there into EAX. This is what moves the address calculated there into here. Does seem like a strange backwards way to get things done, but those are the instructions we have to work with. And if you get down to the hardware, I'm sure there is some logical reason for this, which I don't know. Somehow this is the instruction that was most efficient for them to write, for them to build into the hardware of the processor. All right, so you got EAX and EBX here. And so if you go to location indirect EBX, you'd take this B300, 400, and go to that address, take that memory, and put it in here. That's what it means, this indirect addressing. So this is interpreted as an address, and that value is what gets put in EAX. So you can subtract things, you can add things, you can increment by adding one, decrement by subtracting one, and you have multiplication and division. You have both integer and floating point multiplication and division available if you want them. I've never used them. Things like that I write in C. I did try this in like 1979. In 1979, a seminal paper came out in Scientific American explaining public key encryption for the first time, which was a miracle. And an entire generation of computer enthusiasts, including me, decided I'm going to write a public key encryption routine. So I tried to write things that could handle 100-digit integers in 8-bit assembler, and I didn't make it. And if I had made it, I would have just been I think it was Zimmerman, the guy that spent the next 20 years fighting with the US government because they saw him as having violated export controls by publishing a public key encryption routine that our enemies could use against us. I would have done it at that time because the world should be all able to use encryption, and he ended up having decades of suffering. So I was spared through incompetence from that problem. Anyway, NOP does nothing, 0x90. Use this all the time. Just like you use 0 all the time in math, at first you'd think, why do you need an instruction that does nothing? Turns out to be extremely handy. The only point of it in the original design is that there are certain instructions that cannot be arbitrarily placed in memory. They have to be at a word boundary. So they have to be at location C4 or C8, but not C5. So you have an instruction, and the next instruction cannot be put right after it. You need a gap, so you fill it with NOPs. NOPs do nothing. Take one cycle and go on to the next one. But attackers use it to make a NOP sled. If you're injecting code and you're trying to run it and you're not sure where it is, you can just put like 10,000 NOPs before it. And now if you can guess even close to where it is, you'll hit somewhere in the 10,000 NOPs, and that will do NOP, 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 and run your egg being the attack you want to run. This turns out to be very handy using a NOP sled. So the stack is the memory for local variables and flow control. ESP and EBP point to the top and bottom of the current stack frame. Every subroutine you jump into has its own stack frame, so it can have its own local variables, which exist only while you're running that routine, and when you return, the local variables are removed. They vanish from access, and that's what happens. ESP and EBP are the top and bottom of that string. Push adds data on the stack and makes ESP smaller, and pop takes the data off the stack and makes ESP larger, making the stack frame smaller. So you push data on and you pop it off. You call a function or enter a function, and that will save the current state in the enter a function, save the current state in the prologue, run the function, and then at the end of the function, epilogue I think, it will restore to come back. So you call to enter a function, saving your current place, and you return, which then restores the saved information to pick up where you left off. So that's the prologue and the epilogue. There we are. The prologue is when you enter a function, what moves the ESP and the EBP to create a new frame. And the epilogue is what removes those stack pointer and base pointer back where the calling function expects them to be, and moves the instruction pointer back to pointing to an instruction in the calling routine. And so that is the main reason the stack exists. So you can do this, call a subroutine, and return from it picking up where I left off, except when things go wrong. So you start with, say, Windows running out here, then you double click on Word, so it launches Word here. As a subroutine, then you click on Print, so it calls Print from within Word, and when you're done printing, it returns to Word, and when you close Word, it returns to Windows. And that's how it is, layer after layer, and you're typically 30 or 40 layers deep. And as long as you have enough memory, you can be as deep as you want. But if there's an error anywhere that lets me write something too big, I can overwrite this and overwrite that, and when I try to come back, the data I use to come back is corrupt. And I don't go back to where I should go, but I go somewhere else. So inside each stack frame, you have a bunch of local variables, and then at the end, you have the old EBP from the calling function and the return address, which is the saved EIP. So if any of these variables permits me to write beyond boundaries, I can overwrite the contents of other variables, which is the simplest kind of Stack Overflow, or I can even overwrite the saved EIP, which will cause the instructions to resume in the wrong place and execute instructions that were not the ones the programmer intended me to execute.
Question. So
Yeah.
the address randomization, does it randomize each stack, or does it randomize within a stack? Do you understand what I'm saying?
I do understand what you're saying, and the question is, does address randomization randomly change these? And all it does is it takes one entire program and randomizes it.
Yeah.
And all the pieces move
Not within
together,
the program.
not within the program. And so that means it is fairly easy to find information disclosure vulnerabilities that give me a clue where I am and undo ASLR. There are three general ways to overcome ASLR, which we're going through in 127. One of them is to find a clue that tells me where I am. That was real popular in Windows XP. There was an EBP that you could find that had a number that told you where you were, so it was really a joke. The second one is to use relative instructions. Like you find a jump ESP and you execute that and it will jump to the stack wherever it is. That's called trampolining or return-oriented programming. And the third way to do it is the heap spray, which is bloody brilliant. You take your attack, you add a really large NOP sled, like 100,000 bytes, and then you run like JavaScript in a browser to make thousands of copies of it. You just fill the entire RAM with your attack. And then you jump at random. And the odds are pretty high that you'll hit one of those NOP sleds and run your egg. So it doesn't matter that things are random, just spray it all over the place. Those are all ways to do it.
So the spray is you fill it up yourself.
Yeah.
You force the stuff you're hunting for. You're kind of cornering
You
it.
make multiple copies of it everywhere.
Yeah, but then you're cornering the code you want to attack.
Well, you're trying to add code. On all of these, you're just trying to add code and make it run the added code. So you don't care about the original code. But you have something like a browser that has access to a large piece of memory and you just fill it all. That's the idea. So test will compare two values to see it doesn't change anything. It just, this will set the zero flag if it's zero. So if you want to say if something equals zero, do something else, then you do test and then you do a jump zero or a jump not zero after it. You can do a compare also to compare two things. And jump zero will jump if the last thing resulted in zero, and jump not zero will jump if the last thing resulted in a non-zero value. You also have jump greater than zero, jump less than zero, and all sorts of others. Because it's a CISC computer, it has many, many, many instructions that do almost the same thing. So when you enter C, you've got main. You can put in command line arguments here. This is the number of command line arguments, and this is an array full of all the command line arguments. So you have cat, foo. The first thing is cat, the second thing is foo. Those are the arguments on the command line. There you go, copy foo to bar. This has three arguments, cp, foo, and bar. This is the name of the program, and these are the arguments that will be used by the program to copy a file. All right, I see it's coming up to an hour. Let me see if we're going to get down to the iClickers. We are, good, right on track. Good, we can do the cahoots. All right, which command will change the size of the stack? Okay, push will add something to the stack, making it bigger. Which one is repeated many times in buffer overflows? Okay, NOP, good, the NOP sled. Which command will retrieve data from RAM? Yep, this one moves data from that location in RAM. This one just calculates the address and loads the address without getting the data out of it, which seems pretty silly to me, but that's the way it is. All right, which one will retrieve data from the stack? That's pop, good, all right. And what does this do? Move EAX, bracket EBX. That's it, takes EBX, interprets it as an address, fetches the data from RAM at that address, and puts it in EAX. All right, so these are the winners. So we are 126, and I've got at least 2 projects to show you, and maybe more. So Jasmine, I don't think we talked about this one yet. Didn't do this last time, did we? I doubt it. I'm going to operate on the assumption that we didn't. If I'm repeating myself, let me know. Jasmine is here, and you can download it and run it. It's very slow because it runs in Java. So you always think it's not running. You have to count to like 20 before Java launches. There's a fun knock-knock joke. You go knock-knock, who's there? Java. So, okay. This is like Dilbert. This is humor that will only reach a certain audience. Anyway, but it really is that way. You launch it, you say, damn it crashed, what's going on? It's Java. Java is extremely popular because it runs equally badly on all platforms. So anyway, so you don't have to rewrite your code for other platforms. It will just fail on all the platforms, and that's what saves you a lot of money. So anyway, so this is the simulated processor. This is a very simple, and I made my own version of it, which has a irritating image removed, and it also has lowered the RAM, so it's simpler. So this simulates a very simple processor with only 256 bytes of RAM, and with the registers from the x86 here, and even the floating point registers, although I've never tried using them, so you can put in code and run it here. So if you put code up here, you can put in move EAX1, for example, and when you type it in, it will put a help pane down here and teach you about the move instruction. So it's very nice. And if you get anything wrong, it will turn red and tell you what you did wrong. So it's very useful for you to learn assembly code. And then it will run this. Now, right now, it's not running anything. The green shows the current instruction. This 0 is the instruction pointer 0. Now, one thing that is not accurate about this is that the instructions are actually in RAM, just like the rest of it. And Jasmine has a separate memory region for the instructions, and it numbers them 1 per instruction, and that is not exactly right. Real instructions are several bytes, and they live out here. But aside from that, it's very close simulation and a very good way to learn. And so you can move EAX1, and then I can move EBX2, and then I can move ECX from EAX. Okay, so none of that has happened yet. I've just prepared for it. Up here I can execute. This will run the program right to the end. This will run one command, and this will do God knows what, line at the caret position without modifying the instruction part. I guess, I don't know why you'd ever do that. These are the only two I ever use. Run it all the way or run it one step at a time. So I run one step, and it puts a 1 in EAX. That's an immediate value of 1. Next one will put a 1 in EBX. Next one will take what was in EAX and put it in ECX, so it will turn into 1. Now I can play with the stack. I can push EAX and push EBX. Okay, so when I push EAX, it takes this 1 and puts it on the stack. And the stack is at the bottom of my memory. So the 1 goes there, down here. And when I do the next instruction, it will push EBX, so you see the 2 goes there. That's push. And the green area highlights the stack, and the ESP and the EBP keep track of it. The EBP points to the instruction below the bottom of the stack, which is 256, or 100 in hex. ESP points to the top, 248, which is here, which is the 32 bits starting at that location. By the way, this is hex, and this is base 10. I can change them to be the same. This will make them all hex, or I could leave this in decimal and change this to decimal if I wanted to, and then you will see decimal. Oops, I've sorted by accident. Oh, descending and ascending. There. That changes this to base 10, 248 and 252, like this one. You can make it into base 10 or base 2. All right. So now I push those things. Now I can pop EDX. So the stack, whoops, EDZ is no good, so it turns red. EDX is okay. All right. So now pop means it's going to take the top of the stack, which is the 2, and put it in here. And when it does that, it puts a 2 in EDX, and it changes the stack pointer to 252 down here. The stack now only has 1 word on it. The old word remains on the stack. The 2 is still there. This is data remnants. This is a huge problem. Data you are no longer using is still there. This is true of RAM, it's true of the hard drive, it's true of everything. This is why when you donate computers to a college, you have a big issue. Did you really clean them off? It's true of USB sticks, and it's true of RAM, and this is what happened to Target. Target ran payment processors in RAM, and then they left the credit card number sitting in RAM when they were done with it, and the malware came and stole it out of the RAM. It is like this. there is a data type in Visual Studio since 2004 for ephemeral data like that will remove it when you're done using it. And as far as I can tell, browsers have now updated to that, because I wrote a project for the incident response class like this, and when I did it a few years ago, and I did this at Hope, you could go in a browser, log into Google, and I could go in the RAM of your browser and steal your password. But I can't do that anymore, not with modern versions of Chrome. So apparently they have finally wised up and are using those ephemeral data, so that it only stores your password briefly in RAM and cleans it off when it's done with it. But to save time, the processor does not remove data when it doesn't have to. It just leaves it there because it'll be overwritten when you need it, and when you're not using it, it figures it's harmless because the people that designed it were thinking about speed and they were not thinking about data remnants. So that's push and pop. And so that's the game here. Here's the, we talked about the locations here and all that jazz. So, oh, we should do some indirect addressing. So if I could do move into EDX from location 0. But first I think I'll put something in location 0. So let's move into 0. I don't know if I can do this. Oh, it's letting me do that. That's nice. This is the joy of complex instruction set computing. I can move into location 0 from EAX. I wouldn't be able to do that on an ARM processor. I'd have to put 0 in the register first. So that should load 1 into there. And so it does. That loads it up there. And this should take the 1 out of there and put it here. I think I can, by the way, increment memory directly. Let's try incrementing 0. Nope, can't do that. This is why I'm saying, even with 10,000 instructions, the ones you want aren't always there. It has to be a register, or 8 16-bit or 32-bit memory. I thought 0 was 32 bits. Maybe it has to be 0x0? No? Nope, apparently not. All right, I'm breaking the rules. Okay, that's life. So what I'll have to do, when you know this sort of thing, you do move ECX0, and now increment ECX. Nope, can't do that either. How rude. Okay, so now if I wanted to increment that 1 there, there might be a smarter way to do it, but this is how I know how to do it. I move from location 0 into EDX. Now I increment EDX. Now I move into location 0, EDX. There. Those 3 commands together will add 1 to this value. There might be a smarter way to do it, but that will get the job done in 3 steps. So put it in EDX, make it bigger in EDX, and put it back there. Now I put a 2 there. And your compiler, when you write C, does all this work, trying to figure out which assembly language instructions will be the most efficient at implementing your code. And there are whole layers of compiler optimization, and you can control them with compiler flags. Anyway, that's the indirect addressing. And there's the stack, and there's push and pop. And so here's something that will reverse a sequence. Try that one. By the way, you can just delete this stuff like notepad text and paste in other text. It's very nice that way. So this will put 1, 2, 3, and 4 in the registers. Whoa, I ran it all. Didn't mean to. Let's reset and run it 1 step at a time. Okay, so it puts 1, 2, 3, and 4 in the registers. Now it's going to push them onto the stack, which I emptied by resetting. So it's push, 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 push. So there's the, whoa, there's the 1, 2, 3, and 4 down there. Now it's going to pop them, so they're going to reverse in order. So it's 4, 3, 2, 1. So this is one way to reverse a sequence of numbers. Put them on the stack and pop them out. There are many other ways to do the same thing, of course. And so that's the game here, and here you run this program and get an answer, you can record success. And that's all the Jasmine I put in this class. I had some more in the other class, but I didn't add more Jasmine to this class because I found a nice assembler to play with. Because Microsoft is having trouble today, I could not download Visual Studio, which is what I used to use. Visual Studio is what the pros use to write code, and the problem is it's 5 gigabytes. It is like driving a tank down to the corner to get a beer when you could just ride a bicycle. It's ridiculously huge. It has a million features we don't need. All you need is a very simpler assembler. And since Microsoft was down, I renewed my search and I found a fun thing called MASM32. So MASM32 is a nice, simple assembler for Windows. And I found a good C compiler too, which is going to be used later. So MASM32 is in fact 10 years old. It's all written in assembly. These guys are the total assembler geeks that love assembler. They're super proud of the fact that they use nothing but raw assembler, and you should too. And why did people ever write Windows 95 and all this modern crap that isn't worth having? They should just use MS-DOS and assembler and the world would be wonderful again. So that's where they're at. And so this thing is actually 10 years old and it runs like a champ. You can totally write assembler. And when you install, it screams stuff by for 2 minutes, compiling every bit of it. It's totally written in raw assembler. These guys wouldn't touch a high-level language. It would pollute them. Like, it's just filth. Just take your C and go away with it. So you install this junk, now you can write assemblers, assembly code, and it runs just fine on this Windows 98 that you've been using, and I bet it'll run on any version of Windows, because these guys are super proud of the fact that this doesn't use any of their fancy modern features that are all junk anyway. So there it is, MASM32 editor. Yeah, come on, cough it up. There we are, MASM32 editor is here. Now, you can now put in code, and I found a bunch of tutorials and stole some stuff. So this is Hello World in assembler.
It's shorter in C.
Of course, it's shorter in C. That's the whole point. That's why wimps like C, but the macho, tough people use assembler because it's superior as a cosmic spiritual accomplishment to use assembler. So first you tell I'm using 486, the particular version of old code I'm using, and 32-bit memory model. Here's some include files. These include the Windows API, which we're going to use, which is why this is worth studying, because the Windows API is the king of this class. Malware uses the Windows API, and assembler lets you see how it works. So here's the include files. These should look familiar. User 32, kernel 32, GDI. These are the DILs. And these inc files are the links into the DILs. So it's loading this means it can use user interfaces like Windows. This means it can do kernel calls to affect hardware. And this is the graphic interface to draw graphic things like buttons and stuff. So by including all those, I have the ability to do those things. And that's all just sort of boilerplate. So load libraries I might want. The actual active ingredient is 2 lines here. Print, hello world. And then exit. That's it. Now you had to define a start section that had all this junk. Then this is the code section. There's code section is here, and the start is this area. This print will print characters. Now, CHR dollars just means form a data structure that puts 1 character per byte. Put this stuff in ASCII, and I was puzzled by this until I finally realized it. This is just a carriage return line feed, 13 and 10. So you can specify characters by either putting them in the quotes or by putting the base 10 numerical values here with commas. So this will print hello world carriage return line feed, because you don't have \n for that the way you would in C. That's how you make a carriage return line feed, and then you exit. This is this classic hello world, which is the way all programming classes start. The first thing you do is print hello. And that means you figured out how to compile your code and use your language. So you got to save it someplace. And by the way, one thing I found, as far as I can tell, you have to put every project in its own folder. Trying to put 2 projects in the same folder seemed to lead to a disaster. So there might be a smarter solution, but I just put everything in its own folder. So let's go to Documents and make a new folder. A new folder, okay, called Demo Assembler 1, okay? And in there I'm going to call this hello.asm, I think is the thing to call it. I think I like me to call it ASM. I'm not really sure that's necessary, but that's what I'm calling it. So now that I've saved the assembly language, I now have to compile it. Now there are various options here, but I don't mess around. I use console build all. That will just do everything. If you want to be picky about it, there's compiling and linking. There are 2 separate steps that you can do, but if you don't care, you just build all and it will do the whole thing. So it opens a command prompt so you can see what it's doing. It is now going to build it. I don't know why it calls it an ASCII build, but that's what it calls it. You have to press any key to continue. So it's going to create an object file and then an assembly file. And if you know more computer science than I do, you know the object file has been turned into machine code, but it hasn't been linked with libraries or something. exe file has the whole thing. So, oops, I hit the wrong button. I don't know if it did it or not. But anyway, we'll find out. If it worked, it's project run program. And it won't do anything because it's a console program. It printed something and then quit. So since I have to run it in the console, I'll do File, Command Prompt. That will put me in the right directory. Now if I do a dir, I wrote hello.asm, but now there's something called hello.exe. So I can supposedly run that, and it says hello world. So there we are. Now I'm writing assembly code. So now, by the way, if you close, I think you can close this one, yeah. The other one, where it says press any key to continue, if you close it with the X, it'll close the assembler entirely, which is kind of rude. Anyway, that's the game. So now I make a new file, and let's try something else. You can do everything in here. It's really pretty cool. That's why I'm, so here, I had you save, so in order to give you something to turn in, I had you look at this thing in PEID. Remember good old PEID figures out what program you wrote it in? Well, you'll see what it makes out of this. And the answer is it can't figure out much. This assembly thing does not leave the breadcrumbs behind that things like Visual Studio do to guide it. But anyway, you get some text there which you can turn in to show that you did this. Now, I must be able to make a buffer overflow. I spent like most of the day doing this. I thought it was bloody awesome. So here's a buffer overflow in Assembler on Windows. The best one I could come up with. So let's put in this junk and let's talk about it. So this removed some comments so it doesn't fill it. So I got the include files to put in libraries and stuff. Okay, then I defined 5 string variables. This one is called welcome that says what is your name. This one is called hello that says hello. This is called carriage return line feed. I put it in a variable so I didn't have to type it out all the time. Then I have a buffer which has room for 4 characters, and then I have another thing after it that says all done. And what I'm going to do is put more than 4 characters in here and overwrite that one, and that's a buffer overflow. It's the simplest kind of buffer overflow where you overflow from one variable into the next variable. I wasn't able to get the other kind working because you have to write your own prologue and epilogue. And we could do that, but it seemed kind of pointless. We're going to do that later in C. Anyway, so now this is the important thing is to understand the API calls. So, and this is all important to understand. This is how you store data. You have a data segment and a code segment. And the data segment has these values stored in it, and you can change them. So these labels point to the address where this starts, and then the bytes from that point forward include this, and you have to have an extra 0 to terminate each string, because that's a standard convention. You have to have a null terminating your strings. So that actually takes 5 bytes to store a 4-character name. Now, here's how you call a function. I want to print something, so I push the offset of welcome, the address of this, on the stack, and then I call standard out. That's what you typically do. You put the arguments on the stack, then you call the function. The function's prologue will reserve space for local variables and find the variables on the stack and put them in there, and then use them, and then return. So that will print this variable. So now I go to standard in to read input from the keyboard. So I have to push the offset of where to store it, which is a buffer. So I've read this, but I'm going to write this. And now I told it I'll read up to 100 characters because I want to create an overflow. So I only stored room for 4, but I'm letting it read up to 100, hoping I'll be able to commit an overflow. And this is the same thing that happens in C. The place where you read data is not connected to the place where you store data, the way it would be in Python or Visual Basic or those other high-level languages. So you can make this mistake of having a 1-gallon bucket and putting 10 gallons of junk in it. And then I just print everything out. I print out hello, then the buffer, then carriage return line feed, and then the goodbye, the bye message, done message. That's what I do. So let's compile and run this thing. So it is project. Well, I have to save it somewhere. You have to save it before you can do it. So I'm going to go up here and do demo ASM. Oh, I have to make a folder. As far as I know, you have to make a new folder for each one. There may be some. Come on, my mouse is dying right there. New folder. Okay, demo ASM2. Okay, now I'm going to call this thing buffer overflow.asm. Okay. Now I'm going to do project build all. It's going to show me this screen showing you're going to make those 3 files. I press enter, it does it. Now I'm going to do file command prompt, dir to see what I have. I have a thing called bo.exe, so let's run bo.exe. What is your name? If my name is Sam. It says hello Sam, all done, because there's no problem because a 3-letter name will fit in the reserved space. But if I give it a name like Wilbur, then it gives me Wilbur, and instead of printing all done, it prints R. Because the Wilbur, the WILB went in the name, the U went on the null byte, and the R went into the next variable, and then it wrote another null byte. So it nuked the all done and turned it into R null byte. And I wondered if I could crash it, and I couldn't crash it. I even tried, you know, as long as I could put in.
The R didn't just replace the A of all done, it replaced all of all.
The A?
R of Wilbur.
Right. What happens is I reserved space for 4 characters and a null byte. So this fit in the name, WILB and U, and the R is what leaked into the next name.
But it leaked into the next, but it replaced the
Right, because
LL,
when it wrote this and then the null byte.
Oh,
So it put, so it terminated it.
because it
Yeah.
had an null byte in there.
Yeah, and this one, at first I thought it wasn't working, but it is working. I put in a long name and it said hello, and the next one is not quite as long. There's a few characters missing from it. So a whole bunch of it ran over, but you can't make it crash with this kind of code because it's not calling that kind of subroutine from here. But anyway, that's the joy of a buffer overflow in glorious assembler. And again, you can examine that file and see what function calls it uses. It only uses a few functions in kernel 32. Of course, it's not doing much other than input and output, but it is using a few things like write file and read file and such. Anyway, so because remember, in Unix, everything is a file. So in C, everything is a file. So reading from the keyboard is reading from a file, and writing to the console is writing to a file. That's the way Unix treats everything. Every device is a file. So that's assembler and Jasmine, and I guess that's enough for today. But if you want to work ahead, you can start using Ollie. That's why Ollie is the easiest way to manipulate assembly code. This is a famous old program used by people to cheat on Windows games. You can modify Windows games to give you a high score, make the enemies run slower, and that sort of thing in Ollie debug, and it's been used by teenage script kiddies for years. That's why I wanted to start there. It's really quite easy to see what's going on in a program and mess with it with Ollie, and we're going to do that. That's why I wanted to do this before we do IDA. IDA is the serious professional tool, which is kind of hard to get into. Ollie is pretty much fun and games. It's the right place to start. So that's what we'll do next time is Ollie. So any questions about anything? Well, I guess that's enough for today. I'm going to go to the lab and help anybody who wants to work on campus. And I guess I'll see you in a week. It'll be chapter 8 next time.